Can we kick her off?
You're off the team.
Well, at least I'm adding some diversity.
Everyone likes mango, and that's it. Did we hear Zinglu already?
I think it was a mango, right?
Strawberry.
Oh,
Right.
okay. Strawberry's solid.
And then what about Courtney? What's your favorite fruit?
I'm also team strawberry.
Nice. Okay, so what does this tell us about embedded?
You guys like fruit.
Yeah,
You guys are
Not
healthy.
much. I was just bored. Cool. So, 5 mango. Wow, you guys are savage. Well, Serena, what's your favorite fruit?
Strawberry.
Oh,
Hell yeah. My 2 favorite people on the team. I now know.
wow.
Who was the other one? I missed it. I joined late.
It was Zinglu.
Zinglu, yeah. Zinglu. So, what does this look like? It's a plum, mango, pineapple, strawberry, right? So plum just had 1. Mango is huge. I'll put strawberry here, then pineapple. So it's kind of like a normal distribution. I'm trying to make up ways how this could relate to embedded, but it just really doesn't.
Good segue.
Yeah, thanks. So, review from last week. So we talked about analog, right? A fruit is much like an analog signal. There's lots of parts in it. This is not going well. So what did we talk about? Do you guys want to remind me? It's something like resolution, right? Resolution. Talked about sampling speed. Sampling rate, maybe, is a better word. And what was the kind of rule we sort of talked about for sampling rate?
The
A good
higher,
rule.
the more, better.
Like 8 times more, or no, that's like the standard. Like 2 times more, the minimum.
Yeah, 8 to 10 is good. 2x, 2 times, is the quote-unquote rule, but you're really not going to get a good representation of your signal that way. You want to have at least 8 to 10. And anything else we mentioned? Talked a little bit about a voltage reference IC, right? And then like your analog voltage reference. So that's the maximum voltage your analog to digital converter can sample up to. So you can decide exactly what that voltage is if you want. You can make it 5 volts or 3.3 volts or 2.69 volts. But often if you want sort of a esoteric random voltage, you're going to need a special integrated circuit to do that for you. Right, so that's going to provide you exactly the reference you want. So how do we actually go about doing this inside a microcontroller? Well, what happens is that usually people like to draw analog to digital converters like this. No one's ever really explained to me why, but sometimes you kind of, like if this is the analog side. My main guess is that this kind of pointy bit sort of looks like an op-amp, which is an analog device, and this square bit looks like an IC, which is a square device. That's my guess, but in the end, it's just a picture, it doesn't really matter. So if I'm measuring a signal, right, let's say my analog reference is 5 volts, so I can measure up to 5. Make something like this. And I have my ADC, right, and it has a certain resolution. So let's say our resolution is 14 bits. Paid a lot of money, and we have a pretty good resolution. So what the ADC does is that the microcontroller is not going to read this analog part, right? The ADC is going to convert this analog voltage into a digital value for us. And if it's a 14-bit digital value, it's going to be somewhere in between 0 and 4095. Right? So this is actually 4096 different steps, right? Or different levels is maybe a better word, because you have 0 in there, right? If I had 0 to 5, I'd have 6 different levels, right? 0, 1, 2, 3, 4, 5. So what actually happens inside the ADC is it basically works on a sort of ratio matching system. So let's say my analog voltage was steady, just as an example. So 5 volts max, right? Say it was steady at 3 volts. What happens inside the ADC is it kind of looks like this. So this is a visual representation. This is not actually what's happening inside the silicon, but if this is 5 volts, this is 4095. Essentially what it does is it samples the analog side, right? It's measuring here. It says, okay, I'm measuring 3 volts on the analog side. So it's going to fill up a little bar, right, up to 3 volts. So that's maybe a little bit over half. And it's going to fill up the digital bar. So this is analog. It's going to fill up the digital bar by the exact same percentage. Right? That's all that's happening. So this would correspond to 3 volts, for example, out of 5 volts. And that would be some percentage of the whole range, right? So 3 volts over 5 volts. What would that be in percentage? Maybe 60%. Right? It's going to do the exact same thing with the digital side. It'll fill it up all the way to 60%. So it's going to sample the analog side, right? It measures 3 volts, and it converts it into a digital value of the exact same ratio. So 60% of the total possible digital values, right? Which is 4095. Oops. Right, so what would that be if I did that math? 86 times 4095. So that gives us 2457. So this number 2457 actually represents 3 volts measured by the analog to digital converter. And it's sort of a weird concept because you're relating a number to a voltage, but that's exactly what the ADC does. It takes a measurement on the analog side, figures out what voltage that is relative to the full scale, so to the analog voltage reference that you decided, you put there, takes that percentage and fills up its digital bar. Again, this is a visual representation, not exactly what it does in terms of silicon, but would fill up its digital bar to the exact same ratio, right? And that's the number that it's going to spit out to the microcontroller. This is what you're going to read when in your code you say something like read ADC, right? You're going to call some function, and that's going to spit out 2457 for you because it's measuring 3 volts. What would I get if I were measuring 2 volts, for example? Can someone give me the answer? So if I were measuring 2 volts, and I'm 14 bits, what would I get out of here? What number?
1638.
Well, I'm gonna trust you guys. I guess I could just do the math myself, but that's a lot of work. But yeah, that's it. Super easy, nothing to it. And so you can imagine that if
I think it's 6,553 if it's 14 bits.
6,553. Yeah, I may have skipped a power of 2.
Because 4,096, that's
Is that 12? It could be 12.
power 12. Yeah, that's 2 power 12.
Thank you. Right, pretend I said 12 bits the whole time. Yeah, good catch. Does everyone understand what I did wrong there? So 12 bits means we have 2 to the 12 different levels. And that's equal to 4,095. Sorry, 4,096. And because we include 0 as one of those levels, the maximum value we can have is 4,095, right? So, good catch. Thank you very much. Bits. Cool, that's it. So that's exactly how you would read it, and in your code what you're going to do now is you're seeing this digital value, right? You're seeing a 1638, but you actually, for example, let's say you want to know what that actual voltage was. Well, you can just do exactly what the ADC did, but in reverse, right? To get exactly what it measured. So if I'm reading 1638, right, I do, like I say, my variable is, like I'm sensing the, let's say the pressure of the air outside us. So I have a pressure sensor. And my ADC spits out to me some value, right? It spits out 1638. Well, the way I do it is figure out the ratio on the digital side, right? I know how many bits I have, which is 12, not 14. Right, 12 bits. 4095. So I'm going to fill up my little bar, right? 1638. Figure out my ratio. And that would be 4095, 0.4. Right? Now that I have this ratio, I multiply it by what that bar would be on the analog side, right? And I know that because I know exactly what the circuit gave me. I know exactly what I put as the analog value there. So analog voltage reference, I put as 5 volts, right? I decided that in my circuit. So because I know the full scale there, what I can do exactly the same way is fill up my analog bar, right? So it's going to be exactly the same way. So I know the percentage of my analog bar that I filled. So to get the analog voltage, I would multiply my ratio, 4 times 5, and that would give me exactly what the ADC measured, which is 2 volts. Does that make sense, everyone? It's basically a little game of understanding exactly what your resolution is, so how many different levels you have to play with. So this is from 0 to 4095, so 4096 levels, which you get from the 12 bits. And then knowing your analog voltage reference. Those two things are going to give you the exact ratio you're getting on the analog side and what it spits out on the digital side for you. And that also allows you to reverse engineer exactly what the ADC was measuring if you once you just read a digital value from there. So it's super useful. And we often combine this into just one line of code, right? So what we're going to do is if I had my measurements, 1638 that I got from the ADC, in one line of code, what we usually do is divide by the resolution, so the scale digital readings that we can do, and then multiply right away by the full scale analog. And this is essentially this ratio, right? 0.4 times 5. So interfacing with an ADC is super easy, especially when it's inside your microcontroller, which is almost always the case. But we can also have external ADCs if we want as well. And that's often what we do when we have distributed systems, so like our race car. So what we have, let's go down here. Skip this for now. So for example, in our car, we have, so this is the BMS master. BMS is battery management system, so it takes care of the batteries in the car. And it talks to something called the thermistor expansion board. So for now, let's just draw it as one block, but we'll expand on this a little later. So this board actually has an external ADC on it. So there's a little chip that the BMS master talks to. So this is an example of an external one. It's not inside the microcontroller, which is right here. So it does have its own ADC in here. It's not that it doesn't. It's just that we made a very deliberate design decision to use the external one. So what we do is we talk to it over digital. So we use something called a digital communication protocol. And ADC samples all the analog things here. And in this case, what it's sampling is voltage, right? But that voltage is representative of a temperature. So how a thermistor works is basically a thermal resistor. It's kind of a mashup of these two words, right? So basically, people usually draw them in circuits that kind of look like this. So your resistor, and then you often have a little arrow to indicate that it's variable. So what happens is, as the temperature around the resistor changes, the resistance actually changes as well. And that's really useful because what we can do then is put this changing resistance into a circuit and measure the voltage across it as that changes. And so, for example, ones we usually like to use are 10 kilo ohm thermistors. And what that means is that at 25 degrees Celsius, the resistance of this thermal resistor is 10K. And as the temperature increases, the resistance will decrease, and as the temperature decreases, the resistance increases, right? And so that's a super useful way to like measure temperature, and it's actually really cheap as well. And so we have a bunch of these in the car to measure the temperature of our battery pack, which is really useful. Mahmoud, yeah, do you wanna share your screen?
Sure. Just a sec. Yeah, do you see?
Yeah.
Yeah, so this is the ADC value that it converted from the voltages, and then that's converted to a temperature. The ones that are really high just don't have a thermistor connected to them, but these two are connected. I think it's a little messed, but yeah.
Cool. Yeah, so you can see that 4095 value, which is the max voltage that the ADC was reading at that time, given that it was 12 bits. you share my screen again. So now the question is, why did we decide to use an external ADC, right? Why didn't we just save money, right? Skip all of this, skip paying for this. This is actually a $12 chip. Just a hint if you guys want to decrease that cost next year or something you could do. But why did we do all this extra stuff? Why didn't we just read the voltage off of this? This is an analog value, right? That's all the ADC is doing. Read the voltage off of this and send all that analog stuff directly to the microcontroller, right? This would be analog, sorry. Well, the main reason is because these are in different places, right? This board and this board. This board has a bunch of other little circuits that aggregate all the temperature sensors. And so you need to run some sort of really long wires from your temperature sensing to your microcontroller. And that poses a problem, especially in an electric vehicle. So it turns out that, and you can imagine, an analog signal is much more susceptible to noise than a digital signal. It actually sorry about that. It actually can get a lot more destroyed and can actually ruin your signal a lot more easily than if you use digital signal. So if I send analog across, I run the risk of losing my measurement. Like maybe if I was measuring 50 degrees Celsius, some noise may change it up to 70. Or down to 30 degrees, for example. And so I can't really trust that my measurement is accurate anymore. And how that sort of looks at the signal level, something like this, right? So the noise that the signal is going to pick up is the same. Whether you're a digital signal or an analog signal, that noise in the environment exists no matter what. And it's going to pick it up in both cases. But the problem with the analog signal case is that all of these values are valid, right? So let's say we're just looking at positive, for example. But like all of these values between 0 and 5 volts are absolutely valid for the ADC to be measuring, or for the analog signal to be at, right? And so if you get noise, it's really hard to tell what was noise and what was your actual real signal. Because like if my signal was at 4.2 volts and it had some noise and it spiked up to 4.4, that could totally be a reasonable value. Whereas on the digital side, I only have ones and zeros, right? Even if it fluctuates a little bit, I know I'm still at a 1 and I know I'm still at a 0. And the actual reference for that is that thing we talked about in the first lesson. So the voltage input high threshold and the voltage input low threshold. So basically it says if I'm above a certain voltage, that's a 1 no matter what, right? And if we said that our logic level, so the level which defines a logic 1 is 5 volts, and 0 volts defines a logic 0, and the voltage input high would be something like 4.5 volts, for example. And the voltage input low would be maybe something like 0.5 volts. Right, so any voltage below 0.5, even if it's a little noisy, is still going to be considered a 0, right? And any voltage above 4.5, even if it's a little noisy, right, it catches all that noise that you would catch anyway, it's still considered a 1. And so it's very clear in the digital case what your signal is. You're not susceptible to noise as you are with the analog signal, where It could be 4.2, it could be 4.4. They're both valid ranges and they mean different things, right? But the noise has altered the signal. But on the digital side, even if it alters it a little bit, there's only two options. And it's usually very clear to the microcontroller which option you're at. Unless, of course, you have an insane amount of noise where things are kind of going nuts. And in that case, nothing's going to survive that, right? You should probably shut down the car at that point. So this is why we send digital across those long wires instead of analog, right? It's because if we send analog, we may misrepresent what our temperature is, right? And given that temperature is such an important part of an electric vehicle because your batteries are so sensitive when you're charging and when you're discharging, you really want to make sure those measurements are accurate. And for us, 60 degrees, correct me if I'm wrong, Mamu, is the cutoff for turning off the car, right? So if we accidentally go above 60, is that right, Mahmoud? Yeah?
Yeah, that's right.
Okay, thank you. If we accidentally go above due to noise, we're not going to know if that's real or not. We may have shut down the car for no reason. But also the converse is true. If we actually are above 60 degrees and all this noise from bringing the analog signals across have brought us below 60 degrees by accident, we may be running the car in an unsafe scenario, right? So it's really important to make sure that these signals are as clean as possible. Now, where this noise comes from, that's a good question. Usually it's something called EMI. So it stands for electromagnetic. Oh wow. Electromagnetic interference. So it's usually generated by other electronic components within the vehicle. So it's basically magnetic fields that are present around the signals that provide that noise and can accidentally ruin your signal quality. And if you remember from Jared's lectures, the inductor, right? The inductor generates a huge source of magnetic energy. As it's charging up, it's building up a magnetic field, right? We're going to represent it as an M. That's exactly what it looks like in real life. Big M's are coming up. So now think about it. An electric vehicle, the heart of an electric vehicle is the motor, right? That's the propulsion aspect. But the motor is essentially an enormous inductor. All it is coils and coils and coils of wire, right? So have an motor, right? Inside it, usually there are three phases, right? And electrically, they kind of look like this. People literally represent them as inductors because you just have coils and coils and coils of wire inside the thing. And it turns out that currents are changing really quickly inside these coils, right? This is your motor. And if these currents are changing really quickly, then that magnetic field is changing really quickly as well. Remember, the magnetic field is related to dIdt, the derivative of that current change, right? And so your motor is going to be an enormous source of noise in an electric vehicle. And that's one of the downsides to having this motor so close to all of the other electronics and embedded stuff. That noise is huge. And that's one of the reasons we use CAN, for example. So CAN is a digital signal, right? There's that digital to try and be more immune to noise than analog. But it's also designed for in noisy environments. Designed for noisy. And that's why people love it. It's super reliable. And it's used in almost every single car in the world right now. Especially electric vehicles. Okay, that's an S. We'll move on from that. So back to our original question. Why did we use an external ADC? Well, it allows us to offload that analog stuff, right? It allows us to keep the analog here contained to this board and not be sending any analog across, right? Which we know may be susceptible to noise, especially with the motor nearby. It allows us to just send digital out, right? And that digital is hopefully more robust to noise.
I have a question.
Please.
For like that thermistor board, would it be placed near the motor so there would be a lot of magnetic EMI near that board, so it would kind of mess up the signal there anyways?
That's a good question. It is possible that it messes up the signals like actually on the circuit board itself, right? Like these little traces. But usually it's a lot harder to get at those signals because they're actually laid out on a circuit board. And usually they have a pretty good ground reference on that board. So having that really close signal for ground allows you to be a lot more resistant to noise. And usually what happens in these wires is their return path for the ground is not traveling with them, right? So you may have a ground wire that goes through, but all of the analog signals that go by, they don't have their own ground plane that's coming with them the way they do on a circuit board. So sending those analog wires kind of in free space, not on circuit boards, allows for the opportunity of them to pick up a lot of noise.
Okay, makes sense.
Yeah.
Would you put like shielding on like anything though, or?
Yeah, shielding definitely helps as much as you can. So you can, usually the way it looks is, it's like if I have a little bundle of wires, what I do is I put it in a little, it's like a little, like a sheath that sort of wraps them. So if this is like a little cylinder, it's sort of protecting these wires from the noise trying to get at it. And a lot of times this sheath is connected to ground. So this shield is what they call it. So usually shielded cables try their best to protect the signals that are coming inside, right? And you want to use this as much as possible for noisy environments, but it may not always protect it 100%. So usually the best you can. We're going to have to do this on ours for a lot of signals, especially because we made a mistake, which I'll talk about in a second. But any other questions so far? Does it make sense?
Mm-hmm.
Cool. This is a very messy drawing, so please bug me if something didn't make sense. So the idea was that we put this external ADC on here so that we can just talk over digital and have all the analog processing happening here. We'll talk exactly how that digital process works a different day. So there are a lot of different ways you can communicate digitally the information that you need to do. And different protocols have different strengths and weaknesses in different applications, but for now we'll just assume that it's digital, we're sending ones and zeros across. That's basically what's happening. So let's chat a little bit more about the thermistor expansion board. Tell me if you see any, there's a big mistake we made. First person to bring it up gets some mango at the end of class, okay? So this is the VCU, first of all, right? It says that here. But we actually used two of these circuit boards in the car. We use one for the VCU, right, as the vehicle control unit, so it's measuring a lot of the car signals. But we use the exact same board also for the BMS master. And that's just because they both have a lot of the functions that we need. Mainly that they have the microcontroller, right? This is what makes the car run. This is where the code is held on the BMS master and on the VCU. And if you squint, you can kind of read this chip, right? There's a TMS F70. There's a TI logo. And then there's a model. Very expensive chip. Has 144 pins. And split on the 4 sides like this. And so whenever we want to interface with things outside the car, we'll usually connect wires to these pins here. And in our development, what we've done is just put these little header pins, which is nice for jumper wires, so you can just mess around on the lab bench. But in the actual car, what's going to be soldered there is like a full, legit automotive connector. It's going to have a bunch of pins here. And then you're going to come in with the mating one. And these are going to plug into each other, and this has wires going to the rest of the car, right? So, in case we have a BMS master, and it's talking to the thermistor expansion board. And what we actually did was we split the thermistor expansion board into 3 for the sake of convenience, let's say. This is what we're actually doing in the car, so you can understand. So the way that the thermistor expansion board works is, like we said, we have an external ADC, right? We have an external ADC that does all of the conversion from analog to digital for us, which is nice. We also have a voltage reference IC. We talked about that before. Voltage ref IC. So that actually defines for us an analog voltage reference, which would mean the maximum voltage that the ADC can sample, right? Analog voltage reference of 3 volts. Why was that picked? Well, the designer of this board, a Mr. Will McKnight, he's #1 in our hearts. He did some good math, and he has a really good spreadsheet showing the different voltage ranges of the thermistor at different temperatures. And he found that from 0 to 3 volts is pretty indicative of a wide range of temperatures. I think it was something like 0 degrees to 80. Something like that. If you guys have the spreadsheet for the thermistor, it'd be cool to open that up as well, because I'm pretty sure I remember this number wrong. But it'd be nice to see that curve. So we have an ADC. We have the voltage reference IC, which defines our maximum voltage. We also have these things called muxes, or multiplexers. Right, so sometimes you call it a mux. And basically what that allows us to do is switch really quickly between different signals. So at the high level, this whole thermistor expansion board is responsible for 88 different thermistors. Jared, correct me if I'm wrong here. That may be wrong, but we'll go with this. So 88 different analog voltages that this little ADC has to measure, right? This ADC we picked up here. Now, for example, a normal ADC that you'd pick off the shelf of DigiKey would probably have something like 8, 10, 12 different channels. which means that it can measure 12 different analog signals at the same time, and then relay all those digitally to your microcontroller. And remember, the one we picked was $12, right? And it's actually a 12-channel one. So if we want to measure 88 thermistors, it's going to cost us a lot of money to put that many ADCs, right? Because you need one 12-channel one, then another 12-channel one, then another 12-channel one. Oh, wow, 13. Another 12-channel one. And so those $12 for every ADC adds up real fast. So that's not what we did. We use these things called multiplexers. And so they're super useful because essentially what they do is they look kind of like this, for example, in a circuit or schematic. Physically, it just looks like an IC, right? Just another chip. So let's deal with just an 8-bit one for now. So we have 8 inputs, 4, 5, 6, 7, 8. So 8 inputs. And only one output. And basically what this does is it's a little selector. So based on a control signal that we give it, you can imagine there's a little guy with a switch here inside, right? And so he'll connect the first input to the output. And the output is going to be exactly connected to whatever is attached to the input. Now we change the control signal. You say, no, now I want to talk to the second one. Then it's going to connect the second input to the output, and you're going to be able to read that. Now I change the control signal. Right? I have a different control signal. Now I want to talk to the 6th one. Right? And so it'll keep switching between these as you control it. And usually you want to do that pretty fast. And so basically with one pin, you're able to switch between 8 different inputs. And the way the control signal works is it's just 3 bits. So you have 3 pins here. If I send 0, 0, 0, what's going to connect the first one? If I send 0, 0, 1, it'll connect the second one, right? And the first one will be disconnected. And so forth, right? If I send 0, 1, 0, that's going to be the third one. Right, this one's going to go through. And so each of these has a little code assigned to them. So we could write something just for visualization purposes, like this one would be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1. Right, so whatever control signal we give with our 3 wires, and these are just binary, 0s or 1s, we can decide exactly which input is going to be connected to the output. And so we use a shit ton of these on the thermistor expansion board because it allows you to turn, for example, 8 to 1. 8 to 1. So this is an 8 to 1 mux. Or you can get some that are 12 to 1, get some that are 16 to 1. What's on ours? Do you remember, Jared? Is it 8?
I think, yeah, because I think we have 12 total on our board.
Yeah.
Yeah,
Yeah.
I think we have 8.
Because there's, yeah, exactly. Yeah, so on our thermistor expansion board, we use this one. And so what that allows us to do is instead of needing an ADC, for example, in this small case, that had to have 8 channels, right, and measure every single one of these, we only need 1 channel now. Just with 1 channel, we can measure all of these 8 inputs because we go through the mux. And as long as we're smart about how we select which one that's going through, we can read all 8 whenever we need to. So those 3 boards I mentioned. This is the bottom board, middle, top. Six muxes on the bottom. Six muxes on the top. And our ADC is in the middle. Now, I need someone to tell me how many analog signals would go from the bottom to the mid board, for example. Knowing that these are 8-to-1 muxes, right? How many analog signals are going from the bottom to the mid? 69 is close, but wrong. It's also not close. So on the bottom board, it's measuring a lot of different voltages. It's going through the muxes, right? And then, remember these are 8-to-1, right? So each one is going to send 1 up. So we're going to have 6 analog signals come out. And log. Does that make sense, everyone? I need a verbal confirmation.
Mm-hmm.
Jared's 3D printer. Anyone?
Yes, that makes sense.
Each of these are 8-to-1, so 1 comes out, which is nice. And then 8 come in, 4, 5, 6, 7, 8. So it's cool because now we have 8 times 6, 48. And in the actual board, we don't use a few more, so it drops down to 44. But you can essentially use only 6 channels of your ADC, 6 analog channels, but actually be measuring 48 because you're switching between the different muxes. So 6 analog come from the bottom, and then 6 analog come from the top. So our ADC is 12 channels. We only need 12. Right? And the idea behind this board is that all 3 of these are stacked right on top of each other. So it's a little sandwich. And they're super close by. We're sending analog from one board to the other, but they're stacked on top, so they're literally connected to each other via pins. Top to mid, bottom to mid. And then the ADC converts all this stuff for us and sends digital to the BMS master using something called SPI. Right, we'll talk about that later. Different day. Now this is all well and good, and it's interesting because it combines all of the things we've talked about so far in the lesson. So your analog measurements, voltage reference ICs, GPIOs. Don't forget that. You're also going to need to send 3 GPIOs across from the VCU, right? And that's going to control all of these muxes, remember, right? They had those control signals that we talked about. So someone has to control them, and it turns out to be the BMS master. Sorry, I keep saying VCU. So the BMS master will control exactly which muxes are selected at what times, and then read those analog values via the ADC, right? So that's great. There's those control signals. Now the problem we have in our car is that we have a massive motor, as John knows very well, right? So pardon my drawing here, but this is the race car. And it turns out that our motor is so big that we have to put it this way. So this is the shaft of the motor, spinning like this. And then we have a differential here that goes out to the wheels. So this is a very bad drawing. Doesn't actually look like this, but this is a motor, right? And because it's so big, what we had to do is split up our battery into two separate batteries. So we have one battery here and one battery here. So we call them battery boxes. Just a reference, this is the front of the car. This is the back. These circle things I drew are called wheels. And then the driver sits here. So steering wheel is kind of here. And then the driver sits right here. So because our battery boxes are split, and that's where a lot of the circuit boards are held. So for example, the BMS is in one of these. I think it's the right one, if I remember. BMS is in here. And remember our thermistor expansion board was 3 boards. This would work really well. So remember that this is measuring the temperature of all the battery cells in the car, right? Its job is to give you an indication of exactly how the cells are doing, if they're overheating, if they're on fire, if they're nice and cool, which is good. So this was our top, right, which had muxes. This is our mid, which had the ADC. This is our bottom, which had more muxes. And these were literally just squished on top of each other and stacked really nice. The question now is that we have batteries in both boxes, right? There's batteries in this box and there's batteries in this box, and we need to measure the temperature of all the batteries evenly, right? In the rules it says at least 20% of the cells, but that has to be distributed evenly across the whole battery. So we have this little board sandwich, and we know that this sends out digital to the BMS master. And these are all of those 44 analog measurements to the thermistors. The question now is, how do we split 3 boards among 2 boxes in a way that is as noise independent, as robust to noise as possible? And this is where we made a mistake. Because if you guys can come up with a good solution, that'd be cool, but from what we understood, you only have this one sort of digital communication, which goes to the BMS master. Right, so these can theoretically be far from each other, but you want these to be as close as possible, because remember, this is sending 6 analogs. This is also sending 6 analogs. And these have to cross, right? You have to have some in one box, some in the other box, so you're going to have wires jumping between boxes. Now remember how we said the motor was the biggest source of noise in the car? Well, it turns out those wires are going right beside the motor. So...
My bad.
Yes. It's not your fault. This is an integration thing, right? We are lucky to have this motor because it was free. Same with these batteries. a sponsor was super nice to give them to us. Without that donation of this motor and those batteries, we would not have anything because everything's so expensive, right? So we have to make do with what we have. The problem is that we sort of designed this board without thinking about that. We kind of designed it before this whole plan of splitting the boxes was really made. And so the question now is, how do you split them properly? Do you put the whole stack in the right box? Right, so let's say we do that. So we put the whole stack in the right box. Right, so we have left, and right. And we'll stack. And these have 44 analog signals for the thermistors. Let's show it on this side. 44. And we have batteries in each of the boxes, right? So batteries. So this is nice, right? The bottom board measures all the temperatures of this battery nice and close together. Then the ADC talks digitally. Right, digital to the BMS master, which is the same box. Digital to BMS master. But now how do we measure temperature of the other box? Well, you guys suck it up and go for it, right? Send 44 analog signals across to measure the temperatures of this battery, right? That's a lot of wires, first of all. You want to minimize the number of wires like in your harness, because that's just a huge amount. First of all, of weight. Second of all, it's just really hard to work with in the car. And these are all analog, right? This is not very immune to noise. You have the biggest generator of noise in the car literally right beside. These guys are neighbors, right? Generating as much noise as can be. So this could completely ruin all the measurements. Ideally, we don't want that. You could also do it the other way as well. You could put the whole stack. Sorry, you could put the whole stack on the other side, right? You could put the whole stack on the left. Put it all on the left. And then send the 44 wires the other way. But you're also going to have to send the digital wires because the BMS is in this box, right? The BMS master is in the right box, so it'll need the digital wires for the ADC measurements, plus 44 analog wires back for the rest of the battery. And so what we kind of decided as sort of like best of both worlds, kind of a compromise, right, is to put one in each. So here's the top board, 44, go next to our battery, 4. Right. Send 6 analog over. Remember, 6 muxes, right? They're 8 to 1, so 1 signal comes out of each of them. Send 6 over. And then on this side have the mid and the bottom. Right. So bottom has their muxes. 44, go to measure the battery temperature. And then the mid has the ADC, right? And that talks digital to the BMS master. Right, so at least it's not 44, but it's still 6 analog, right? And that's what we wanted to prevent. And that's the mistake we made. So we're going to do our best to shield the heck out of all of these.
Can I ask a question?
Yeah.
What about just having 2 thermistor expansion boards
Yeah,
and then
and
just have the digital wires in between?
oh yeah, I was gonna ask as well. What's in the middle board? Because if it's just the ADC, or I'm not sure what's actually in the middle board, you can just put the ADC like a different a cheaper ADC on one of them, or no, for both of them, and just have 2 boards, one on one side, one on the other, and it'll be digital.
Yeah.
Yeah, and then you can maybe do it with CAN or something, and it'll be more resilient to the noise
whatever
that's
the-
going over the motor.
Whatever the ADC outputs.
Yeah, so that's definitely an option. You can just double, right? That's something we played around with.
Is the middle board just an ADC, or is there something else there?
It's basically, yeah, it's the ADC and the voltage reference IC,
Oh, okay.
and some
So you
filter.
need 2 of those.
Yeah, so you can put a second one, right? And then you send digital instead. So it depends how much extra cost this is and all that stuff too, right? So what we're gonna do is test it first, see if we survive this process. If not, you can duplicate it. Send 2 SPIs, right? And get an SPI here, an SPI here. And both go to the BMS master. It's definitely an option.
Is there any
It's-
other?
You won't be able to send CAN because to generate CAN signals, you need to be able to generate the different message IDs and the CRC bits. So you would need a microcontroller. So you would have to have an extra BMS master here, right?
Unless you get an ADC that uses CAN, I guess.
Yeah, if you find one, let me know. I've never been able to find one.
Really?
And yeah, I've also looked for like SPI to CAN converters and all that stuff, and those aren't really a thing.
Interesting, because there's ones for Raspberry Pi, right?
Converters?
Like you take in CAN and then it converts it to SPI for the Raspberry Pi.
Yeah, but you need a microcontroller too, right, to understand it.
Well, yeah.
Questions? We'll open up this Excel doc on this one.
Is there any other problems like this because we had to split the batteries?
There are other problems in the sense that we have to send a bunch of wires across. Not the same analog problems, but just annoying
Okay.
problems, some problems.
Are they all digital or whatever?
Most of the rest are digital. Some are some power ones for contactors.
So are the UART wires for the BMS going to be going over the motor?
That's
Like
a
the
good question.
BMS lives?
Yeah, so in the right box, I think it's the right, I could have it backwards, but if it's not the right, then it's exact mirror, but you have BMS, put it down here. BMS masters here. talks over UART to slave. Slave has a daisy chain to the other slave. And this is all within the right box, and then we have to send the next daisy chain across. So this goes across the boxes, and then the other two slaves are here.
Could you, I mean, I don't know if this is possible, but I guess you could just have like one tunnel in between the battery boxes or something.
Yeah.
That's super shielded.
Yeah, I had the schematic for between the boxes before, and it was something like 20 to 25 different wires going across. Just because
you
you
have
had to
like a
split
pipe,
it.
have a
Yeah.
pipe in between.
We'll use one of our chassis tubes and just shove 20 wires through.
Yeah, honestly.
Yeah, sounds like not a bad idea.
Yeah.
No.
Yeah, but again, we haven't even gotten this far in the car, right? We haven't built the battery boxes. We haven't connected all the electronics together. We haven't finished the firmware. We haven't spun the motor with stuff. We've only spun it once. We haven't tested it with the throttle pedal. There's so much stuff that still needs to go on in the embedded and electrical parts. So we can even get to the point of testing this and seeing how noisy it gets and if it's better to go with 2 ADCs and all that stuff.
For sure.
So-
Cool.
Fair.
Any more questions? So this was sort of a little case study on our car and how the embedded system works within it. So it's pretty interesting because the embedded system ties so closely to the electrical that you can't really know one without the other. If you're designing the electrical system, for example, the thermistor expansion board, you need to understand how that's going to impact embedded. If they're going to need a lot of extra processing with 2 different ADCs and 2 different SPI modules, if it's going to affect the signals electrically going through a noisy environment, if you're going to need another microcontroller or another converter, they're all intertwined. And so it's really useful to be that bridge between both teams, that you understand how one decision impacts the other. And it's interesting because the mechanical layout is what introduced all of this as well, right? So the whole car relates to itself in different ways, and understanding each piece is really critical to make things work, you know. And this is just one mistake, right? There's so many others that we've made that we don't know if they're fatal or not yet because we haven't tested. But could be or could not be, we're not sure. That you guys can test out, build, improve upon, and make really reliable. So it's your guys' car, and have fun making it run.
Thanks.
Thanks.
Cool, that's it. I know we teased digital to analog converters last week, but I wanted to go over this, so we'll do the DACs next week, and then hopefully do a little bit of PWM as well. Okay, thanks guys.
Nice. Let's do the embedded meeting.
Thanks.